So what is our aim is we want to build a knowledge, we want to address this problem with VLMs and knowledge distillation and early exit combined. So knowledge distillation and early exits are intended to reduce computational cost. So let me give you an example. I want to trim a 10 minutes video down to a 1 minute. 10-minute video will have 600 frames, and even if inference is 10 milliseconds per frame, it will be it will take at least 1 minute for the model to compress it down. So we want to reduce the computational cost for the inference, and we can try to make it a product ready work. So our aim is that we will imply knowledge distillation and early exit, and we want the computation inference time to reduce, and at the same time we want an insignificant decrease in the performance. We can check the significances through p-value and other tests. So that was our crest of our project work, and this we will start with the seminars paper, so that now we can actually understand the seminar work more related to our project. So the first paper is joint video summarization, moment localization by cross-task sample transfer. This was published in CVPR 2022. We will aim knowledge distillation. We will focus more on the knowledge distillation part of the work. This is the only paper yet till now that has addressed knowledge distillation in video summarization. Same problem statement, we have an input and we will have a trimmed video down. So the motivation is that already existing data are very small. If you see, all of the 4 prominent existing data are hardly having 170 videos, and the average duration is no more than 2 to 3 minutes. So there is a scarcity of data set and scarcity of data, low resource. So how we can actually how we can overcome through it. This work has addressed it. So they have used the second correlated task, that is moment localization. So they use the second correlated task moment localization data and try to use it for their model for summarization task. One of the critique is that they have not mentioned that the imbalance of the data, since the localization data have around 12,000 videos, and while the summarization has hardly 200, there is a high imbalance. They have not addressed how they overcome the imbalance of the data sets. Second is they devised an important propagation algorithm, and third is they have proposed a collaborative teacher-student model using a mean teacher strategy. We'll focus more on the third contribution since it's aligned with with knowledge distillation more. This is a methodology, looks very clumsy, but we will go through step by step. So the whole methodology is divided into 4 modules: summarization, localization, propagation, and teaching module. As mentioned before, we will be focusing more on the teaching modules. Summarization and localization modules are pretty simple. You take video, divide it into 1 frame per second, and pass it to Google Net and extract some features. So for the corresponding frame VI, we have a feature HI. Now we pass it to a feed forward network and to produce an importance map. This importance map is a 1 cross n. N is the number of frames in the video, and this denotes the importance of per frames. So that same can be done into the localization module. So this was a summarization module. This was a localization module. So now we have an important maps for both of the modules. So the localization is like a kind of thing. If I ask for the summary of this module, this video, it will try to capture the whole essence of the video. So it may take 1 frame from here, second from here, third from here. But in the localization, I have a query, that person putting the bag of groceries down. So it will only capture that thing and won't be considering the meaning of the whole video. So that is the second correlated task they want to use. Yes, sir. That is the second correlated task they want to use and improve the performance of summarization. So now what we have observed from the importance map, that they do not have any temporal informations. They do not capture any temporality. These are like 1 frame for the importances for that particular frame only. So now they introduce a propagation module. So they include something like a span range. So that so to introduce temporality. But one of the critique is that they could have used 3D CNNs. That could be, I guess they should have provided it as one of the benchmarking. So what it takes the importance map and make a richer representation of the importance map. from I, this is a I, and they make it to JSON. So what they do for all of the frame, it iterates in a loop, and for each of them, it sees the left one, the left view, and the right view. So now they call this one as a scan region. For each of the frame, they take the left view and the right view. That is a hyperparameter scan. So if I am at the, let's say, this frame, uh, no sir, they do not take it from the inference map. No, no way. And from the hmm, the higher importance could be the one end, and the second higher importance could be the second end. Uh, that could be more of a dynamic, and yes, this is more of a static. Like they do not provide any argument, but my intuition says that they have taken data static so that making the models little simpler. So now this is a scan range for this particular frame, and now for each frame, they do the cosine similarity for all the frames in the scan range. The cosine similarity results are here. So let's say this frame is highly related, highly similar to this frame, and now they just take the they multiply both of them and take the average. So what is their intuition is that if a frame is very important in the scan range and it is highly similar to it, then that should affect the score of it. So if there is a frame, let's say this one is highly similar to this one, we can say highly similar to this one, and it has a good importance, so it should affect this one too. So now once we have updated all of them, for all of this is the intermediate importance map. This was the original importance map. Now they take the simple average of them, but before taking average, they put some Gaussian distribution. The Gaussian distribution is for to approximate the influence of the adjacent video frames with increasing distance. So that is the code here. We take the offset, distance offset, and put in the Gaussian frame. So now let's before starting with the teacher module, the main teacher module, what the summary of their work is then they took importance map from the summarization and localization module, and in the summarization module, since temporality was missing, so they applied a propagation module so that the richer that is a better richer representation of the importance map. So now they begin with teacher module, the main teacher module. So the main teacher have student model and teacher model. Student is actively updated using gradient descent, while while the teacher is not updated via gradient descent, but via something known as exponential moving average. We will discuss it in the next slides. So one advantage of using exponential moving average over gradient descent is that it will be smoother results. The parameters will be smooth, and second is that the computation will be less costly, since we are not doing any back propagation here. So this is a generic mean feature model algorithm. You have a labeled data. Second is a unlabeled or correlated task data. You do the cross entropy loss, that is a supervised, and then there is a constructive loss where they see the parameters from the student model and the teacher model, and either you can see the difference through the mean square error or KL divergence. And next, they make a total loss. This total loss, they backpropagate and upgrade the student model, and with this exponential moving average, they update the teacher model. So the teacher model at t+1 iteration is supervises for the sir some student model. So this one is the loss function for student model. This one, this cross entropy loss. So this is a cross entropy for the labeled data student model, and this is a constructive loss that is between unlabeled or the correlated task, that how much different it is from the teacher and the student are producing. That is also for the student model. The teacher 1 for the teacher model is some gamma with parameters of the teacher model at kth iteration plus right. Yes, sir. Feature was label data. Yes. Okay. No, students, even if we assume that a teacher was trained on a perfect data, but the student data is actually noisy. So when we are actually updating the teacher's model, teacher's parameter through student, we want to give more importance to the teacher part because we are assuming that teacher is not noisy. So we will give less if let's say gamma is student part. Uh, yes, sir. That is one of the thing we are actually including on our project. Yes, sir. That is true.
And also in the paper, so they have mentioned that gamma used to, even if when they are trying this, they are still considering values very close to one, but
That is. Hmm.
that is like one of the critic and
Yes, sir. Yes, sir. So maybe one of the reason could be that we have very low data. So The DL is very less. Label data is very less. Yes, sir. Yes, sir. We will have to then look at deeper in it. So now, yes, sir. Yes, sir. Yes, sir. Now, before going into the training, actual training, these are some notations. This says that these are neural network for the teacher model for the localization network. This is a summarization for the teacher model and so on. These are nothing but video features that are extracted through Google Net, and these are importance map, and this is the important map through after that algorithm we discussed propagation module. So the overview is that is no, sir. The original important maps, when we get this thing, features, we pass it to the feed forward network, and then we get the score 0.6, 0.8, those things. Yeah, that is trained on that data set. Okay. Okay, this one. So actually, the feed forward, this doesn't have a feed forward network. This passes through the propagation module algorithm, which we discussed, uh, which had Gaussian and scan range. The knowledge distillation is here, the teacher student model. In the next slide, we will have. Okay. Yes, sir. Yes, sir. S is student and T is for teacher. Yes, sir, for the importance map. These are the importance map that is generated by a student teacher network, and that is the importance map is generated by the student network. We denoted by here by S. So many networks. That is like the critic of the paper. Like, yes, sir. Yes, sir. Yes. No, sir, I'm sure. These are neural networks. Okay. Okay. The detailed intuition was missing, but the architecture is there. So I will share that how it works. What we want to learn a student model from the teacher model for the localization. So whatever we will get the difference in the importance map, we want to reduce it. We want the importance map of student to look as similar as the teacher. So this was on the localization data. Next one will be on the summarization module. Again, we want the student to be as similar as to the teacher. So we'll take that difference. Difference is a KL divergence difference, and that will be a part of the loss function. So now that will be a cross difference. So I was talking about this. The intuitions are not actually mentioned that why exactly this they are doing it. Like they have tried all of the possibilities, but they should have shown an ablation study that after removing one possibility, the results are going down. Now again, they are trying to make the importance map of summarization data from the student to be as close to the localization for the teacher, and so on. Like I've denoted the color notations for understanding. This was on localization data, and similar task can be done on the summarization data. So we want the teacher to be close to the student in the summarization. So this is denoted by yellow, and so on. So we then they try to optimize all of these models together by adding all of the differences in the loss functions along with the cross entropy loss, that is supervised loss. This is nothing but this actually denotes the KL divergence, important map of summarization of student model. This is student model, and importance map of summary to teacher model. This is the teacher model. So in the evaluation metrics also they have used an F1 score that Yes, sir. F1 score, and I have a critique that why not use correlation metrics like Kendall Row and Spearman's Row, which other works have actually used it. Between the generated summaries and the gold label summaries. Awesome. Yes, sir. Yes, sir. Okay. Okay. But many of the paper even till now have using those correlation metrics till then. Then I will have to see that why. Okay. Correlation metrics. These are the results, and they should have actually what they did. They use all of the LM and SM data to train the architecture, but showed only the result on the SM data, that is summarization data. But they should have actually tried that architecture to see the results on the localization data. So that actually know the generalizability and of the architecture. They have not used any vision language. There is only one paper in 2023 NeurIPS that used Flip as a vision language model. Else, everyone used CNNs in this domain. So the conclusion is that because of the data scarcity, they use a second correlated work. Then this was the only paper till now that uses a collaborative teaching teacher-student model. Even like we can actually dive more into and like do more research on the teachers model, knowledge distillation part. And they defined the one algorithm, importance propagation algorithm, and exactly the experiment showed effectiveness. These are references. So there is also one blog which I have written for the domain of this work, that how summarization, like video summarization, is not yet what we call like not yet producible in industry. Right. Yes. So now Utkarsh will go on. I one thing which I like discuss what the data set. Like the data set is small and the videos are like only visual centric. Nobody took it from the like perspective of. And second thing is that this work was started in 2014 where there were no transformers, so people never knew that we can like, process the text so efficiently. And also with the after 2022, the YouTubes and those of the videos, so much of the content. So mostly this class was seen only through CCTV surveillance or those things. Yes, sir.
Dr. Man, now being a teacher on this evidence is that which was published in the main points that we highlights of this paper are they are using unlimited for a unified the meaning to this paper. The paper has discussed yeah. So previous to this paper, no paper has discussed the early exit model for both encoder and decoder in a transformer model. So we'll see. And also they have also mentioned that they are using uh, loss for each and every layer in the decoder model. So before starting to the paper, we'll see an observation that they have made. So these are actually pre-existing early exit methods that were there prior to this paper. The blue one is actually MUE, which is the content of the paper, and others are also early exit methods. So basically, these are some other early exit methods which are also which do not consider both encoder and decoder. So all the other methods do not consider taking early exits from both encoder and decoder. Uh, some of them also require auxiliary networks like classifiers to implement. So the main contributions of this paper is the novel architecture that they are proposing, that they have proposed for both encoder and decoder. The decomposition of encoder model is also one of the important things that they have mentioned, they have introduced in the paper. One more important thing is the layer-wise task loss. So in the decoder model, they are not using the complete task at once. They are considering loss at each layer and then taking an aggregated value of that. Also, one more contribution that they have mentioned is that they have seen up to 50% uh, uh, time reduction in inference with minimum performance drop. Uh, so let us start with techniques that are used for reducing inference time. So there is one knowledge distillation part. One other is mentioned in the paper is quantization, and other is weight proving. We are also using knowledge distillation for the training part. This is a combination of both the knowledge distillation and early exit. In the paper, they have mentioned a lot of existing early exiting works. So I have done a little literature survey on that. Most of the focus has to be on the exit placement and confidence metric part. So this paper introduces completely new idea for both the things. We'll quickly look at the complete overall architecture, and then we'll go one by one to the modules. So this is the overall architecture. This is the decomposition part. That is the novel architecture that they have mentioned. So during training, they train the complete part, and while inference, they decompose the original encoder part into two different modality oriented encoders. These are exactly the same encoders which was trained, but these are just the duplicated copies. The main idea is they have noticed that for different modalities, the confidence metric that they are using, that is the similarity of layers. Uh, for different modalities, different early layers can contribute in the inference part. So, for example, layers can take an earlier exit than the text part. And also, one important thing here we have to see is that uh, prior to this, nothing nowhere was done on encoder, exiting from the encoder, because anything taking out from the encoder still has to pass through the decoder part also. So this is what they have like. Yes, yes. No, sir. For not for all the layers, for the decoder part also, they are finding the similarity in the layers of the decoder, and taking an early exit from the decoder also. So early exit here they are taking early exit from encoder and decoder both. Prior to this, none of the works showed any getting model for both encoder and decoder. So this is overall how a transformer model will work. So basically, they have two modalities: image and text. Will pass the image through a resonant, pass the text through through any tokenizer part, convert them into tokens. Here, the tokens are decoupled positional, decoupled positional embeddings, because for the text we are using 1D relative positional bias, and for the image we are taking 2D relative positional bias. EI represents any ith layer of the model, and I to J represents a subset of the encoder from I to J. So once this is passed, we get the final output is EI1 to N, I naught T naught, which is the input. We'll move to the part of the decomposition. So here is how they are decomposing the encoder part. So the original trained encoder is now exactly duplicated for both the modalities, image and text. And image embeddings are passed to the image encoder. Text embeddings are passed to the text. This is all during the inference time. Text encoding are passed to the text encoder. We take an early exit from some PH and QH layer from both the models. We concatenate the embeddings and we get this IPTQ. So the output will be EI to P for image and EI to Q for text, and we call it as we just denoted by C. When this whole C is passed to the cross attention model of the decoder part. I0 is the input from the ResNet, the input embedding. Yes. So this has to be the PF layer, and this is the QF layer of the encoder. Yeah, E12P is that part, and E12K is this part. Yes, we'll discuss it. Yeah. So the decoder part is considering of two blocks. First is self attention block. The other is cross attention block. So initially the self attention gets the inputs from the encoder that we got. Then the output of the self attention concatenated with C that we have discussed earlier is passed to the cross attention block. Right? Hence we get for ith iteration. Since this is a sequence to sequence regressive decoder, so we can generate more than one tokens from the decoder, and hence we can run the whole thing multiple times for one iteration of encoder. Yes. With the yes. Yes, this I is the ith. Uh, this I is the ith iteration. So ith token generator, the output from the I minus one is token generated, and S is the layer. So for S0, the first decoder layer would be there. C is the uh, initial output here. So this is how the overall architecture would. Yes, sir. We'll discuss. So this is how the overall architecture would look. The second part is the early exiting idea, whole overall idea. So through rigorous experimentation, as they have mentioned in the paper, they have come to a conclusion that for both decoder and encoder, for in the initial layers only, they are able to see there is a spike in the similarity value. So there the similarity is less in the initial layers. Then after a certain point for both encoder and decoder, the similarity values kind of saturate. So they have come to an idea that after this certain layer, we will be able to take outputs from for the inference part. We can take outputs from those layers. And for the similarity, so basically this becomes and this is simple cosine similarity. So this becomes for image it becomes I and I minus one. So I similarity between ith and I minus one h layer. This is basically similarity computation between two layers, two consecutive layers. And for text, it becomes ETI minus one. For decoder, it becomes the output of decoder and at the ith layer and I minus one layer. For the theta value also, so here the theta value, there also uh, we have a threshold at this value. So after a certain threshold, the threshold of similarity value, they will exit from that layer given the value. For theta also, they are going for a heuristic function where beta and tau are the hyperparameters. Uh, the whole idea behind this is decoder, since it is a sequence to sequence autoregressive model, the earlier outputs are more erroneous. So they don't want the earlier outputs to exit very quickly when the similarity values are uh, like too less. That is why they are storing this theta, which is the threshold for the similarity values. And when they are moving forward, yes, yes. For the this theta p is the threshold. This value they have like put from experimented from 0.5 to something. So they start in this heuristic manner. Yes, 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 sir. No, no, up. saturated. Yes. This is how, like, experimentally they have come to this conclusion. The third part of this whole architecture is the loss, layer-wise loss, as we have discussed. So they are taking the cross entropy loss with each and every layer instead of taking the loss at the end, and then they are aggregating, bridging the values from all the layers. So this is the algorithm that we have discussed already. So how everything is working. Input tokens from image and text both are fed to their corresponding encoders. They run the to all the layer, like they start from all the layers. If the similarity value is greater than theta, then they exit from that layer, and then the whole output is fed to the decoder. Decoder is run for and whichever number of tokens we want to generate from here. S is that, and for all the layers I2 and whatever the number of layers. This is the overall algorithm. Just previous layer. Some, yes. Yes, sir. No, no, sir. Yes. So that is one thing we can, like, that is one of the critique that I have mentioned, that we can also use a learning based or adaptive method for the cross entropy loss only. This is the overall loss that for the decoder part. So instead of taking the loss at the end, they are calculating the loss at each and everywhere. This is the loss which was used for the tuning part. So the overall loss function, this is the overall loss function. Right? So this is made from these uh, losses which are uh, from each and every layer. So this is a summation all the layers. So their loss function for the training was designed in this way. No, 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 no. Yes, yes, sir. This was used for the training during the training objective. Uh, so here, some of the experimental details are there. There is, yeah. So they have also defined one new valuation metric that they call expected time reduction rate. These are some results that the paper shows. Here we can see that they are reducing the time by 40% in a captioning task and almost 50% in so this SNLID is used for classification and tailing task. These are some results only. These were the critics that I was talking about. Pairwise similarity is again very heuristic function. We can try to learn this value. Uh, Again, yeah, this threshold value, similarity threshold value is still uh, beta and tau are still like fixed values. So these can be hyperparameters that we can learn. And also, they have not mentioned any adversarial study on that. So they could have done an evaluation study on adversarial data also. There is a possibility that for a noisy data, the similarities go very high for some certain layer, which is actually not the uh, layer that we want to tame. These are the takeaways. So, whatever throughout whatever we have discussed, we are trying to do attain this real world inference benchmarks needed. So, which is what we have prepared also benchmarking dataset for the submission also. So here on we can discuss the project implementation that is really going on.
We have also submitted for this what is this product proposal. We have submitted in the link, and we have made some of the progress in the implementation part. So first of all, we didn't have any data set, the real world data set. So I actually, with my friend, a freelancer friend, I made a 500 curated data set. So these are all of the present data set till this date. So all of them, and this is our data set which we have collected. So it has a, yes, sir. So these are the some statistics of the data set. So I've made it like more like interesting comedy, travel events, how to style, and one of those things. So coming to the baselines, that data set which we have curated are now fed into the all of the existing models. This is the paper which we discussed. This was in the paper CVPR 2024. Evaluated the benchmarks. These three paper are also like from same authors, and so yes, so this was the result. The F1 score was very less for 23. So on my data. In their data, in the existing data, their reference score reaches up to 60. But on yes, our data includes text modality. So when the annotator was annotating, he also took care of the text modality. The my friend and I, like I gave him guidelines. So like also, so we all three did. Yes, sir. So then there is a multi-stage knowledge distillation. We have like we have the code ready and it is running. Yes, sir. This is our loss function. We have a teacher, student, and there is a mentor. So that since the divergence is yes, sir. So that is all from our side. So there is like very minute source which happened there. How?